Okay, so as far as the exercises for this chapter go, you're filling in a lot of the details of the discussion that we had in class. So go through that. That's very important to make sure that you've understood the argument perfectly and, well, grapple with these details. It's been a hard chapter, but an important chapter. Okay, so I want to give a brief summary of what we've achieved and what we've done. So one of the results that we obtained is we said that there was this quantity, the wave function in normalization. It was a probability, Z lay in the interval from 0 to 1. And good. Then we were able to say that the interpretation of that probability is that it creates a single particle state with probability Z. So when you act with your field, you're not certain that you'll create a single particle. You'll only create a single particle with some probability Z, which in general is less than 1. So what we said was, well, that's no good. We want our field to create a single particle state with probability 1. So we rescaled our field. To get the physical field, we said take Z to the -1/2 and multiply that by the field phi. So in fact, the field that we would observe, the field that really does create a particle, is phi p, the physical field. After rewriting the Lagrangian in terms of the physical field, we find that the Lagrangian has got 3 parameters, Z, M, and G. Now, we don't know what those parameters are. The things that we do know, we know the physical mass of the particle. Experimentalists can measure that. We also know the strength of the coupling. So, for example, for the electron, that would have been 1.6 times 10 to the minus 19 coulombs. It's some number that experimentalists measure, and they've measured all kinds of interactions between pions and nucleons and all sorts of other elementary particles. This is something they can measure. And then also we want our field to create particles with a probability equal to 1. So we want to eliminate Z, M, and G in favor of 1, the physical mass and the physical coupling. To do that, we need 3 equations which relates Z, M, and G to 1, MP, and GP. And we've worked out what those 3 equations are. They are both expressed in terms of the Fourier transform of correlation functions. The first 2 conditions come from the Fourier transform of the 2-point correlation function. Okay, so here we've got the 2-point correlation function, and this 2-point correlation function you can see as a pole at the physical mass squared. So that's our first condition. So sum the Feynman diagrams to work out the 2-point function. After you've evaluated the sum, check where it has a pole. Whatever value that is, set that equal to MP squared. Then work out the residue of that pole, and whatever you get, set that equal to 1. That gives you 2 of the equations that you need. For the last condition, you would calculate the 4-point function. I should stress, again, it's the 4-point function of the physical field. So you'd have phi p of x1, phi p of x2, phi p of x3, phi p of x4, and then you'd calculate the Fourier transform of that 4-point function. You want only the connected piece, you want to amputate the external legs, and you want to evaluate it at some very specific momenta, which I have listed for you. Once you've done all of that, set the answer equal to minus I times the physical coupling times 4 factorial. That's the 3rd equation that you need. Using those 3 equations, you can completely get rid of Z, M, and G, and everything that you calculate will be expressed in terms of G physical and the physical mass. Now, when you do naive calculations in terms of M, G, and Z, you do get divergent integrals, and there are infinities which appear. After you've completed this process of expressing everything in terms of the physical mass and the physical coupling, none of the infinities survive. They are all eliminated through this procedure. So this procedure of eliminating Z, M, and G for 1, G physical and the physical mass, this is what is known as renormalization. It's often expressed as the idea that you're removing infinities. I hope I've convinced you that that's the wrong way to think about it, that you really should think about this as simply expressing the theory in terms of quantities that are actually measured. Let me just stress here, go back to your notes. These should all have been 4-point function of the physical field. Okay, very good. Okay, guys, that brings us to the end of this important chapter, and I hope you now have an understanding of renormalization.